Jayson here from ELEK Software. Have you ever worked with standards like IEC 60287 or a cable manufacturer or a specialized piece of software ready to calculate cable ampacity and realized that none of the standard methods actually match your project? Maybe it was a bridge crossing or a HDD bore or a duct bank that didn't fit any of the standard methods that were available. Most engineers in this situation will either guess, they'll over-design, or they'll scramble reaching out to technical support, or they'll stall your project entirely. This is precisely what this video is about. A simple multi-step calculation project that solves these problems. I've been using this same process on real projects for more than 10 years and I've trained numerous engineers on the same process. It's based on engineering judgment combined with the fundamentals of IEC 60287 to deal with non-standard situations. It's now inbuilt into ELEK software and used by engineers all around the world on projects ranging from substations to data center connections. Let's walk through one example. So there is a small story behind this scenario. So it's a railway bridge crossing, and the engineer reached out to me and wanted to know how he could calculate the ampacity for this particular installation condition. So it's two 3-core 22 kV multi-core cables installed inside a plastic duct and then installed on top of this cable ladder support, and there was a specially designed cover on top of the arrangement. So the situation was a railway installation where the cables needed to be heavily protected from vandalism actually. So I'm going to explain how to use the multi-step process to get the ampacity of the medium voltage cables inside the duct installed on this special cable ladder arrangement. So the first step in the process, step 1, is to calculate the base cable ampacity. So that's a single 3-core 22 kV cable that's unenclosed. We need to know the cable ampacity for this situation first. So that's been worked out with a software model to be 636 amps. That's our base situation. Next, step 2.1. We need to figure out what would be the ampacity of a single 22 kV multi-core cable, the same cable type, installed inside the same duct from the original installation. So this would be the same duct size that would house two 3-core cables. So this is the size of the duct. This is one of the cables. Now what happens inside the duct is the cable heats up some air inside the duct, and that causes heated air circulation inside the duct. The duct material itself also adds an additional thermal resistance. So the ampacity for a single 3-core cable inside this large duct would be around 543 amps as worked out by the software model. So the effective derating would be this ampacity divided by the base case rating, which is around 0.8536 is the derating of one of these cables installed inside the same duct. The next step is to work out what would be the ampacity of installing two of these cables side by side. Actually, we should assume that they are touching inside that larger duct. So we'll use one of the other IEC 60287-2-2 calculation methods for groups of multi-core cables. We will do the calculation where E is equal to 0, the cables are touching, DE is 112.5. Now, the theory in this calculation method says that if the ratio of E divided by DE is larger than 0.5, then there'll be no derating or thermal proximity effect between these two multi-core cables. In other words, they won't mutually heat each other in air if they are adequately separated. But these cables are touching, so there'll be a derating caused by these cables being in contact. So the effective ampacity of two 3-core cables grouped as touching with E equal to 0 in air is 610 amps, as calculated using a software model based on IEC 60287. So the effective derating caused by the two cables being in proximity is this ampacity divided by the base case ampacity, and this is the derating factor. So in conclusion, for this installation condition, the effective or overall current rating for this situation equals the base cable ampacity multiplied by the first derating factor for the effect of the duct, and the second derating factor, which is the effect of the groups of circuits. So it's 636 amps multiplied by that derating factor 0.8536 multiplied by the second derating factor 0.9591, and the effective overall derated current capacity for one of these medium voltage cables installed in this non-standard installation condition is 521.3 amps. So if you're dealing with complex cable installations and you're not sure how to apply IEC 60287, use the multi-step process. It's simple, logical, and it's been used across many different projects. If you'd like to see how the process is automated inside our software, there's a link in the description to the free trial. Remember, standards are there to assist us, but we still must utilize our engineering judgment to complete our cable system designs. Happy calculating, and I'll see you on the next one.